puzzle?
Yes.
Number 17?
Yes.
That's peroxides. I'll usually mention something about that at the very end. We didn't cover it. When you put in peroxides, the answer is essentially you get the reverse radiochemistry. Why? It's a radical reaction at that point, and we can discuss it a little bit later.
What is
Olefin, that's just an old term for an alkene. Olefin was mentioned on the first page, on the first side somewhere. Under worksheet, it said alkenes, or in parentheses, it said olefins. There's a few predictive products, etc., on the alkene page. I think I want to let you, we'll move on. We'll do those a little bit later. Let's move into stereochemistry. Keep going with that. Once we look at stereochemistry, we'll go back to some of those alkene reactions and look at them again. But before we begin stereochemistry, any questions? Any lingering questions? Any additional questions? We have the outlines on blue, and then we have the set that I sent to you for printing out. Stereochemistry. Yes?
I just want to make sure I understand this. On this page, you have solutions in there as lightweight.
Correct. That's the one that can take on more positive charge because it has the two rich friends, the two sp3 carbons. And thus that's where the nucleophile added. That's also the same place we formed the carbocation that wasn't actually formed. Okay, the puzzle. That's good review there. Stereochemistry. Okay, guys, top of the hour. We'll get started. Stereochemistry warm-up. Okay, lots of good questions. Lots of good questions. Alkene reactions down here. You'll be looking at those, predict the product, but also include appropriate stereochemistry in your answer. I've got a list of daily questions here. Stereochemistry daily questions. So there's some. Included in stereochemistry is our alkene stereochemistry. Everybody watch the video. We have the cis-trans, more specifically E and Z. Alkenes can be stereogenic. Not all of them are. You'll be able to recognize when an alkene is stereogenic and what that means. And so the very first question here is an E or Z question. E or Z. There you go. Okay, stereochemistry is very important. Stereochemistry makes a difference. For example, the difference between cellulose and starch. They're both polymeric saccharides. The only difference is in cellulose, both bonds to the oxygen which links the two sugar units, I've never heard that go off, are equatorial. These are chair conformations. Equatorial. Down would be axial here, yeah? But in starch, the linkage between the two units, one is axial and one's equatorial. This is stereochemistry. Because they're connected at the same place. They have the same connectivity. It's just the orientation from that place. That's a huge difference. Our bodies can digest starch. We can eat starch. You can't eat cellulose. Trees. Stereochemistry makes a huge difference. So quiet in here. Okay, here's a nice diagram, flow chart, whatever, to distinguish between isomers. You can look back at this for reference as we move along. Isomers have the same formula, two types of isomers, constitutional and stereoisomers. Two types of stereoisomers here, with some specifics written in. For example, cis-trans, that's a type of diastereomers. Reference. Stereochemistry makes a difference. This is a drug called thalidomide. It was developed to treat nausea in pregnant women, given in the late 1950s, early 1960s, mainly in Europe, England. But it caused birth defects. Babies were being born without limbs, particularly arms. Underdeveloped arms, and this is a photo if you can see it on your handout. They were called lovingly thalidomide babies. What was going on here? When the drug company developed the drug, they tested one stereoisomer, but when they started manufacturing it, somehow the other stereoisomer became manufactured. And the other one ended up being a teratogen, which means that it was toxic to the fetus. It was bad science, but the difference was stereochemistry. Stereochemistry makes a difference. Some nurse or female doctor identified what was going on eventually, and they pulled the drug, and President Kennedy, very few in the United States, it was mainly in Europe, but this lady won an award from President Kennedy or from the United States for determining what was going on here. Okay, there's some intro, there's other things there. The blue sheet, our outline. And we'll look at chirality. There's my version of chirality. Read it, read your textbook version, etc. Chirality, also known as handedness. Okay? My hands are chiral. This represents a chirality, chiral objects. Chiral meaning that the mirror image is different. Okay? Mirror image in my hand would be this. Just looked in the mirror, it would see this. Yeah? Okay? Are they the same or different?
Different.
They're not the same. Only this one will fit into the right-hand glove. If I tried to put this one in the right-hand glove, it wouldn't fit. That tells me they're not the same, correct? Okay. Yeah, mirror images that are not the same, we call this chiral. Okay? Could you have mirror images that are the same?
No.
Yeah, you could. What's the mirror image of this paperclip? If that looked in the mirror, what would it see? It would see this looking back at it. Right? Do you agree? Yes, it would. Okay. Same or different? These are the same. So why are these the same but these different? Comes down to a plane of symmetry. If something has a plane of symmetry, its mirror image will be the same thing. This has a plane of symmetry. I can cut right down the middle of it and have the same half on each side. Does my hand have a plane of symmetry? What if I cut right down the middle of it? I'll have a thumb on one side, no thumb on the other. What if I slice right through this? Like right through there, real thin. Will that be a mirror image? No, I'll have a palm on one side, a top of the hand on the other. Now if I had palms on both sides and sliced right through there, it would be a mirror, it would be a plane of symmetry, but I don't. So ultimately, if something has a plane of symmetry, that's what we want to look for. Because if it does, it won't be chiral, meaning the mirror image won't be different. If you cannot find a plane of symmetry, that means the mirror image will be different. So ultimately, it's like, where's Waldo? Where's the plane of symmetry? Okay? What about compounds? Enantiomers. We call these enantiomers in chemistry land. Now, we call these right, not tan. But if these were chemicals, we would say these would be a pair of enantiomers. Okay? Well, let's look at enantiomers of some compounds. What about the enantiomers, and what does R&S mean? Enantiomers of this compound, 1-bromo, 1-chloroethane. Let's draw that compound. I'll draw it, maybe then we have to redraw it. Ethane, that's just 2 carbons, right? There's 2 carbons. 1-bromo, 1-chloro. Ethane, is that right?
Mm-hmm.
Okay. But we can have, let's see here, I might want to do this very specifically. Pull out my notes. I have notes. I'm sure I did somewhere. I usually like to just do things on the real time, so you see me sort of thinking. I'll do it like this so I get things very precise. Okay. Let's draw, you can actually have enantiomers of this. 2 different forms, like a right hand and a left hand. Let's draw the 2 forms. I'm going to draw them a different way here. Let's see, what if I draw the chlorine? This carbon here is the main carbon. We can often star that carbon. That's the so-called chiral carbon. Chiral carbon. There's the ethane. Here's the 1 carbon. There's the chlorine. I need to put a bromine. What if I put the bromine? That's tetrahedral carbon, yeah?
Mm-hmm.
Okay, 2 in the plane, 1 forward, and 1 back. Let's draw in the H so we can really see it. And then the H is going back. There's the compound drawn like that. This compound, drawn with the carbon being shown the tetrahedral. Yeah? Okay, let's draw the mirror image. If this looked in the mirror, this is like it's looking in a mirror. And this is the mirror over here. What does it see? Well, it's going to see, let's see if we can make this look nice. Hey, racist today. Let's see, this would be like that, correct? This would be like this. Do those look like they're mirroring?
Yes.
The answer should be yes. You should see that. Okay? Like it's looking back at it. Yeah? A bromine forward. There should be over there a bromine going that way. Okay? If you're my mirror and my hand is like this, yeah, you would be me, with the hand would be over there. Yeah. Okay. There we go. So are those the same or are they different?
Different.
Well, if you named them, they would both have this name. 1-bromo, 1-chloroethane. Stereoisomers always have the same name. But guess what? Same compounds always have the same name. You said they're different.
Mm-hmm.
How do you know they're different?
Because if you try to put them on top of each other, like your hands, they won't be the same.
And if you try to put them on top of each other, what's the chemical term for trying to do that?
Oh, I don't know.
Superimpose. If you try to superimpose them, they won't stack. For example, how do we know my hand's not the same? Well, if they are, you should just be able to stack them on top of each other. Well, look, I can't. Thumb's over here, thumb's over here. How do you know they're not superimposable?
Because if you,
Should we go to the model?
that would be nice, yes.
Okay. Chlorine, green, bromine. What color do you want bromine to be? Blue? I think you said blue. Chlorine, green. Straight up. Methyl alkyls tend to be black. Bromine, blue, coming forward. And the little H is going back. Now these are actually supposed to be eclipsed, but okay, but hopefully you see that. There we go. Okay, that's that one. Now let's make this one over here. Chlorine straight up. Methyl this way. Bromine coming towards you. It's over here. And the H going back. There's that one. And this is, bromine is blue. So it's like that. Okay? Are those mirroring each other?
Yeah.
The bromine is, okay, the black is in the plane. So the black's in the plane. Mirroring each other. Yes, see how the bromines are mirroring? And the blacks are going away. If I stand in the mirror like this, my projection should have a arm going that way. Okay? Okay, there we go. There are the two on the board. Same or different? Well, can you superimpose them? So can we stack? Greens line up, but look, the black and the blue don't line up. Well, we can make the black and the blue line up. Like that. Right? Well, look, now the greens don't line up. They don't superimpose. They don't stack. It's just like the hands. They're different. Mirror images that are different, we call this compound chiral. Now, if we switch, if we disconnect, and do this, now they will superimpose because you got that one there, you want one just like it? Well, there you go. There's one just like it. But I had to disconnect. Okay? As is, they're different. This is a chiral molecule that has handedness, two different compounds. Now they have the same connectivity, have the same exact name. So are they constitutional isomers? No. They're stereoisomers. They have different projection, same connectivity to different projection. Stereoisomers have the same exact name, they only differ with some type of stereochemical descriptor. So how can we distinguish between these two? We use R and S terminology. R and S defines the arrangement at a certain carbon. By the way, we didn't note this. If I just gave you this, how would you know it was chiral? Well, you could build the mirror image and see if they superimpose, but you could also do what? You could look for Waldo, or 4 different groups, but you could look for Waldo, which means look for what?
Symmetry.
Plane of symmetry. Does this have a plane of symmetry?
No.
But what if I cut right through here?
No.
I got blue on one side, I can't remember what that was, bromine and chlorine on the other, so that's not a plane. What if right through here? No. I mean, you cannot cut right through here. No plane of symmetry, that tells you that the mirror image is going to be different. Right? Well, when are we going to get no plane of symmetry? Whenever you have 4 different groups on a carbon. 4 different groups on a carbon is going to lead to, there'll be no symmetry at the carbon. You have to have 2 same groups on carbon. For example, if we have 2 blues, 2 bromines, now we have a plane of symmetry. Now we can cut right through here. Okay? But if you have 4 different groups on one carbon, you're not going to find Waldo. And thus you're going to have a chiral compound, meaning the mirror image is going to be different. How do we distinguish between mirror images? We've got to be careful. There's two different ways. One way is for the compound as a whole. R and S is for a carbon, is one particular carbon. Let's do that. Okay, here's how you do it. Remember when we did, well, when you did E and Z. How did you do E and Z?
Oh, the atomic.
Atomic number. Yeah, you gave priority. Same thing here, atomic number. On the carbon, what's the highest atomic number? Bromine, chlorine, or carbon?
Bromine.
Bromine is 1. What's next?
Chlorine.
Chlorine. What's next? Carbon. H would be 4th. With the low priority group in the back, you look at 1, 2, 3. Is it going clockwise or counterclockwise? Counterclockwise. The answer is
S.
S. That carbon has an S configuration. What does this carbon have? Well, what's 1? 1, 2, 3. With the low priority group in the back, is 1, 2, 3 clockwise or counter?
Clockwise.
1, 2, 3 clockwise. This is R. I remember R because clockwise is right. Turning right. So we call one S and one R. Now that's enough to distinguish the whole compound. Because this here is S. Here's your name. That right there is your name. And this compound is what? R. A stereochemical descriptor. The same names except one's S and one's R. Both of these are hands except this is right and this is left.
So would you ever see R trans, blah, 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 blah?
Yeah, but the R and trans stand for different things. R is for a carbon, trans would be like for an alkene or something. You can have both in the same compound. You can have, a compound could require multiple stereochemical descriptors if it had multiple stereogenic sites. Enantiomers of 1,1-dibromoethane. What if this was bromo? I mean, I hopefully need to spend much time on this. Is this carbon chiral? What's a chiral carbon?
No.
A chiral carbon is a carbon that has no symmetry. Mostly due to having 4 different groups. Does this carbon have any symmetry at it or not?
Yes.
It does. I mean, if we make them both here, that carbon now has symmetry. You can cut right through that carbon. So that carbon is not chiral. Chiral is an asymmetric carbon. No symmetry. So we would not star this and call that a chiral carbon. It's not chiral. There's symmetry there. There's actually symmetry over here. The whole compound has symmetry. And so the mirror image is not going to be different. If we made a mirror image of this, or if we can do it real quick, hopefully I've already kind of explained it. That would be, I guarantee you it will be that, because there's no choice. That's why you put it any way you like. Is that the mirror image? Yeah. Same or different? Look, they're the same. Mainly because I'm able to turn this, because the groups will line up. Mirror image is the same. Enantiomers of there's no enantiomers of that compound. It's like there's no enantiomer of this paperclip. Mirror image is the same thing. Okay, enantiomers have identical physical properties, such as melting point, boiling point, dipole moment, density, etc. I mean, the dipole of this, the directional dipole of this is going to be a mirror image of that dipole. It's going to be the same magnitude, and it's, okay? Exceptions. They rotate plane polarized, I call it PP light, in equal but opposite directions. Kind of a random thing. I don't know, Louis Pasteur maybe discovered this. Equal but opposite directions. If it rotates PP light to the right, which is also known as the positive direction, that's the dextrorotatory isomer. Can be labeled as D. If it rotates PP light to the left, or the negative direction, that's the levorotatory. Left, levo, L. Note, R and S has nothing to do with D and L. They're totally independent of each other. Okay? One is based on structure. The other is based on rotation of the light. The two enantiomers I raised, one was R and one was S. Well, one is also D and one is L, because they were a pair of enantiomers. And a pair of enantiomers rotate PP light in equal and opposite directions. One of those rotates it one way and one rotates it the other. We'll say this again, but the two compounds that I had up there on your paper, that's a DL pair. If I agree, that's a DL pair? Because one's D and one's L. Just like if I had two people here and one was a boy and one was a girl, I would say, hey, there's a boy-girl pair. It's a DL pair. Okay, another, they interact with chiral objects differently. Well, you know this since you were 2 years old. Your right hand is chiral because here's the mirror image is different. This interacts with chiral objects differently. A glove is chiral. Mirror image of a right-hand glove will be the left-hand glove. Okay? Do these interact with a glove differently? Yes, only this one will slip in. This one will not. That's the idea of they interacting with chiral objects differently. What about a mitten? You know the difference between a glove and a mitten? They both go into a mitten because a mitten is not chiral. The mirror image of a mitten is going to be the same thing. So they'll both go into a mitten. Now think about that. More scientifically.
I have a question.
Yeah.
Is there a way to determine which one is D and L? Like,
You have to do the experiment
Okay.
and shine the light and see which way it rotates. You can't tell from structure. You tell R and S from structure. We'll do more. I don't think we're doing polarimetry in lab. Are we doing? What are we doing in lab? Let's go ahead and make sure we know. We've got a different lab tomorrow, right? I think we're doing bromination of transtylbene.
Yes.
Yeah, it's a bromination reaction. Yeah, we're not doing polarimetry. There is a polarimetry lab in the lab manual if you want to look at it for some of this stuff. We're not doing it. It's very good because it gives you a chance to look at the numbers. Okay, we'll be doing calculations on the next page. Okay. This is very important. This is why thalidomide was toxic. Only one enantiomer will bind to a chiral receptor. This is basically an example of this here, because receptors in your body are also chiral. Okay? Which is why one enantiomer may be an effective drug, but the other may not. Actually, same physical properties for enantiomers. Well, smell could be a physical property. Enantiomers, though, tend to have different smells. That's interesting. For what? Well, what's the mechanism for smell? The molecules go into the nose, and what? They interact with a receptor. But the receptor is chiral. It's like you have a right-hand glove in your nose. Okay? And then in come two hands. Well, only the right hand is going to interact with the right-hand glove. And you'll get that smell that is produced from that interaction. Where the left hand will only interact with some other receptors, and you'll get a different, okay? So that's an example of chiral things interacting with other chiral things, and actually you can get different smells. Okay, but also, drug receptors, and that's what happened with thalidomide. One enantiomer apparently avoided some receptor because it just didn't fit into the glove, okay? Where the other one probably went in and started reacting with some receptor because it fit nicely in, and it led to bad effects. Okay, what about enantiomers of 2-butanol? What is 2-butanol? Well, it's a butane with, what do you think on the second carbon? Yeah, it's like this. This is called 2-butanol. You could call it 2-hydroxybutane, okay, but this is named as an alcohol. All right. Does this compound have a chiral carbon?
Yes.
Which is usually identified by a carbon of 4 different groups.
Yeah.
Yes, and we can usually star this, okay? By the way, I starred some carbons in previous lectures in your notes. Yeah? Okay. Could there be different projections here? Let's see if we can draw them. Let's see here. Boom, boom, boom. What if we put the OH forward? That is 2, right? Here I just flip it. Here's the 1, 2. I just turn it around. Okay? We could draw it like that because that is a tetrahedral carbon. The mirror image would look like what? Boom, boom, boom. And right here, yeah? And it doesn't matter. You can draw the H over here to make it truly mirror, but it's there. Are those mirroring? Other than that one's a touch bigger? I mean, yeah? Okay. Same or different?
Different.
Do we need to make a model and see if they superimpose, or do we have a way to just, how do you know they're different? Yeah?
Because there's 4 different things and they're mirror images, so there's not a plane of symmetry.
Yes. If a compound has 1 chiral carbon, that will ruin the plane. There will be no plane of symmetry for the whole compound. Now, if it has multiple, sometimes you can have a plane of symmetry. If it has 1, the compound is going to be chiral. No plane of symmetry. Okay? Both of these are 2-butanol. How can we distinguish between them? R and S. Okay. What is this one here? At the carbon. Oxygen 1. Which is 2? Carbon with another carbon or just one? Just carbon? Yes. You've looked at the EZ video? How do you determine that? Keep going. Questions on that sheet? Backside, particularly at the bottom, E and Z. 3. What's 4?
The hydrogen.
We're showing H going back, so with the low priority group in the back, what do we got? R? How about this?
S.
It better be S, because guess what? The mirror image of R is S. Just like the mirror image of right is left. I'm holding up my right arm. You be my mirror image. No, I'm holding up my right arm. Well, that would be the mirror. Hopefully, if you look in the mirror, you don't have the arm going that way. Okay. I'm holding up my right arm, but you're holding up your left. The mirror image of right is left. Okay? The mirror image of R is S. It better be S. Or it's the same. But we already kind of hopefully know it's not the same. Is it S? 1. What's 2? Counterclockwise. Low priorities in the back. What is it? S. Ah, but both of them are bold. And the previous one was bold and one was... No, it was the same over there also. Okay, that's right. That's right. Don't worry about that. Some students say, well, that one's bold and it's R, this is bold, so it's R. No. No. If that's R and that's S, 2-butanol, what is this?
That would be R. Right? I think it'd be R.
What is that? Is that some other one?
No, there's R.
What is that one?
It's the R.
You
Is
just
it
R.
2-butanol?
Yes.
Yeah, it's 2-butanol.
Yeah, it's R. It's just flipped back.
Can there be a third version?
No.
I mean, mirror images. There's only, can there be a third in here? I mean, in your mirror at home, is there a third there too? No, there's no third. There's just you and the mirror image. Okay? What do we want to put in front of this one?
R.
R. A lot of times this is put in parentheses. Yes? Yes. This one and the one on the end over there is the same thing. Do 1, 2, 3. RF. 1, 2, 3. Clockwise, counterclockwise. 1, 2. Counterclockwise, so it's.
But the H is in
Oh, the low priority group has to be in the back, is it?
No.
Where's the H, which is the low priority group?
It's in the front.
Forward. If it's forward, you just reverse your answer. Now your book will tell you to do all this. Just reverse your answer, okay? If the low priority group is coming forward, instead of counter, you just say it's clockwise, R. Now if you were on the other if you were over there looking this way, the H would be towards you guys, it would be away from me. And with it away, I would go 1, 2, 3, and it would be R if I was on the other side. Yes, it's R. Here's a little thing. If you keep your backbone the same, you see, the backbone is the same here. If you keep the backbone the same, you could just switch your bold to dash, and you will get the enantiomer. Now these, the backbone is not the same. These are actually the same exact compound because this is where the backbone has just been flipped around. And if you take this with the H forward and flip it, then the H will go back. Okay? So that's that one there. We can also give these different names. This is R-2-butanol. We also have some data. For S, the rotation is 13.5 degrees. This is called a specific rotation. 13.5 for S. So this is S, 13.5. So, is it D or L?
D.
Yes, D. 2-butanol. Could be another name for it. Or we could call it S-2-butanol. What other could we call it? You usually don't mix them. I mean, you could, but usually it's just one or the other. But you could also call it what? Remember the plus-minus sign? D would be to the right, that's positive. Call it positive 2-butanol, D 2-butanol, or S 2-butanol. This one would be what? R, L, or negative. The negative and the L mean the same thing. The R is totally different. That refers to structure. Again, please don't think D always goes with S. They're totally independent. Sometimes D will go with R. S is for a specific carbon. D is for the compound as a whole. Identify chiral carbons in the compounds below. If the compound is chiral, show each enantiomer in a perspective drawing, such as this. Label each as R of S. Is this compound chiral? Not chiral. Why? Yeah.
Oh, no, it's not.
Not chiral.
No, it's two carbons.
The most common way to tell the compound's chiral is to locate a chiral carbon, an individual carbon. Is that carbon chiral?
No.
No. This and this is the same. They both come and end at the same point. It's the same. And because of that, you see a plane of symmetry right through here. You see a plane of symmetry, mirror image is the same thing. Not chiral. Mirror image of that is the same thing. Like the paper clips. How about this? Chiral carbon anywhere. Is both ways around the ring the same? Okay, chiral or not?
Not. No.
No.
Because it's only got.
Do you see a chiral carbon?
No.
Which is also known as an asymmetric carbon. Does it have an asymmetric carbon?
No.
Is that a chiral carbon?
No.
No. What's the geometry of that?
Planar.
No, planar. Something that's planar has a plane of symmetry.
It only has one configuration.
It only has one configuration. In terms of mirror images. Now, it could have diastereomers, cis-trans, but not chirality. It's planar. The plane of symmetry here is the board. That if the compound was a little thick, and it is, because an atom is, you can cut right through it, just like right through the board. Not planar. How about this guy? Yes, that's a chiral carbon, because it's got 4 different things attached, and if you go this way, it's different from going this way. So please do that, the rest on your own. Show each in a perspective drawing and label each as R or S. You will not be able to do D and L because you don't know you don't have enough information to do D and L. Optical activity of enantiomers. We said enantiomers rotate pp light. Question.
I guess I just don't understand why the middle one isn't chiral, because it's connected to a carbon with 2 hydrogens and then a carbon with 1 hydrogen.
Yeah, this is not the same, but that's planar.
It doesn't have 4 groups.
Anything that's planar, you can slice right through it. Now my hand is planar. The problem with my hand is I got palm on one side and top of the hand on the other. Assume I had palm on both sides. Then I could slice right through it and I'd have a planar symmetry. Like a piece of bread, it's the same on both sides. It's yay thick. If you had a good enough saw, you could cut right through it and you'd have 2 pieces of bread that would be done. Something that's planar has a planar symmetry. So, a chiral carbon has 4 different things attached. Because of that, a chiral carbon must have what type of hybridization? Tetrahedral, which is not planar. Okay? The carbon doesn't have 4 different things attached, but that's a different answer. You're looking for, well, I see that, but still, why is it not? It's because it's planar. Okay. So, optical activity is the idea of the compound rotating pp light. To what extent does it rotate? That's the optical activity.
So if a chiral carbon has some tetrahedral, so it's always going to be sp2. So like if a carbon isn't sp2, like
Yeah, an sp2 carbon is not going to be chiral because an sp2 carbon is planar. So, how do they rotate? How do enantiomers rotate? What if you have mixtures? If it's a pure compound, you could just give the absolute rotation like we did for 2-butanol. What was it, plus or minus 13.5? Yeah, it's plus or minus, right? 13.5. What about mixtures? Mixtures. Okay, a 50-50 mix of enantiomers gives no net rotation of pp light. That is, the mixture is not optically active. Or we can say optically inactive. A 50-50 mix doesn't rotate pp light. First off, such a mixture is called a racemic mixture. 50-50, racemic. Or just racemic, sometimes called racemate. Why does a racemic mixture not give any rotation of light? It's because they cancel each other out. It's not that the enantiomers aren't rotating, but one enantiomer rotates, what, maybe 13.5 to the right? The other enantiomer rotates 13.5 to the left, and where do you end up at? 0. Now, when you do the experiment, you just see 0. And so you're like, this mixture's not rotating. Well, it's because they're canceling each other out. A 50-50 mix gives no net rotation. It's optically inactive. Okay? So that one's easy. It's 0. What's not as easy is if it's like a 70-30 mix. How do those rotate? Okay. First off, terminology. An enantiomeric excess, known as EE. This is a common method for describing the amount of enantiomers in a mixture when it's not racemic. The EE is the excess of one enantiomer that exists beyond racemic. Let me try to explain. Thus, a mixture that has a composition of 55% R enantiomer and 45% S, as this ratio of R to S, is said to have an EE of 10% R. That's how we describe this mixture. I mean, you could describe it like that, but this is another common method. We need to know what it means, 10% R. What did I say up here? It's the excess beyond racemic. Let's look at this. You got 45% S. What would cancel this out and be racemic? 45 of this one. if you consider that. 45 and 45 would cancel each other out. What would you be left with of S? Ten percent of this one, after these two cancel out at 45, 45, 10% is left.
You mean 10% off the ratio?
I'm sorry.
Oh.
Yes, that should be R, because R is the greater one. After 45% of that cancels 45% of this, you're left with 10% of R. That's what the EE is. The amount left after racemic cancellation. Now, your book will probably give you some formula that I've never seen. Okay, you can work the formula if you want. That's how I do it. Let's do some examples of this. What is the EE of a sample that is 70-30 DL? Okay, see, we can also call them DL if we know the information.
40D.
I think you're right. What'd you get?
40% D.
EE equals 40% D. Because 30 of this cancels 30 of this. And you're left with what? It's just numbers here. It's what you're left with. 40% of the greater one, 40% of D. That's the EE. Let's see if we can go the other way. A mixture is said to have an EE of 60% D.
80-20.
Yeah.
What is the ratio of the two?
80-20.
Speedy Gonzalez got it.
80-20.
It'd be 80-20. 80 to 20. Because you want to set up a ratio that has a difference of 60. Let's check ourselves. If 20 of this cancels 20 of this, what are you left with over here? 60, which is what? Okay? What other answer could you?
90-10 would be 70, 70, 30 would be 50.
Yeah, but if you have,
It's only out.
They got to add up to 100.
Right.
Tell me another. Think about it. Let me know. What other answer other than 80-20 would work for that? Think about it. Let me know. Okay, that's how you use what an EE is. It's a common way to tell. Okay. What if it was 100% EE?
It'd be all one.
That's when it's all one and none of the other. What if it's 99% EE? Hey, I've got a mixture, it's 99% E. What's the ratio of the enantiomers?
991.
No, that would be 98% EE. Wouldn't it be 99.5 to 0.5? Yes, it would be this.
Oh, yeah.
Because when 0.5 cancels 0.5, what are you left with?
99. Yeah.
That's not magic. That's math. Okay, let's look down here. Let's bring in rotation. Determining the rotation. Other than 100 to 0. If it's 100 to 0, this is just going to be the stated value, like some constant. Or you could determine that and get to that point. Let's see. If it's 50-50, we know the rotation is going to be 0. That's racemic mixture, right? Okay. Here it is. Only the excess beyond racemic rotates. Because we say this cancels this out. What are you left with? This, which we call the EE. But the EE is what really rotates, because the other just cancels it out. So the EE is really your rotation. Thus, a mixture of 80 to 20 RS, which has an EE of 60%, right? That's a 60% EE. will rotate 60% of max. Let's say max is 20. Okay? Well, 2 of this cancels 2 of this, and you're left with 60. While this is canceling, this is the only thing that rotates. But it doesn't rotate 100% of max, it only rotates 60% of max. And 60% of 20 is what? 12. So instead of a rotation of 20, you'd have a rotation of 12. Okay, I didn't do plus or minus or whatnot. Let's do an example. What would be the degree of optical activity of a 60-40 mixture of 2 butanol enantiomers? I gave you the rotation earlier. I think it was plus or minus 13.5. Was that right?
Yeah.
What if you had a 60-40 mix? What would be your rotation?
So 2.7. Right.
It'd be what percent of 13.5?
It'd be 20%.
It'd be 20% of 13.5. So it would be 1.35 times 2, 2.7. 2.7. Okay, positive or negative though?
Negative.
Which one is max?
Negative.
R,
Yeah.
I can't remember, was R, D, or L?
It was L.
R was L?
Yes.
So L is negative. So it should be negative 2.7. Is that the right number of sig figs? What do we have? 13.5. Can we put another number there? Is that right? Specific rotation. Is that right? It's 20% of max. 10% is 1.35. Multiply that by 2.
Is the unit degree? Or is it not a unit?
Thank you, yes. Yes, it's degrees. Okay. What about going the other way? Can we determine an EE from a rotation? Let's try A. What is the EE of a random sample of 2-butanol if the specific rotation was measured to be negative 10.13? First off, since it's negative, which one is the major one? It's rotating more towards the left, so L is major. I mean, yes, if you get rotation more one way than the other, that's the major one.
75%.
And L was that RS.
L was R.
R was negative S. So R. R is major. We know that much right here. What is the ratio? Okay, how do we need to do this? We're really going backwards. 10.13 we need to know max. What is max? 13.5
Negative.
plus or negative. I think we want to know what percent of this is. We want to know what percent is this. 10.13 is what percent of 13.5? 75%? 75% of max, is that right? Is it?
Yes.
I'll take your word for it. If it's 75% of max, what's the EE? Well, EE is what rotates. It's 75% EE. But what's the ratio, though? What's the ratio of the enantiomers? 75-25?
Yes.
No.
It's 87.5 to 12.5.
87.5 to 12.5. with 87.5 being R and this being S. There's your ratio here in enantiomers. The mixture is 87.5% R. It's not 75%. 75% of the mixture is not that. An EE is not, okay, there's a difference. I'm sure you see that. There's your ratio. We kind of went backwards because you could have started here, right, and said the EE is this. And since this is the EE, you're going to get 75% of max. 75% of max is 10.13. Make sure you get your plus and negative right. Okay. We would have did some of that in lab. Take a look at that lab. There you have a mixture of, not ibuprofen, but naproxen sodium. Some of you maybe have taken. This is Carl. It's supposed to be just 1 enantiomer. You do the lab to prove that it's just 1 enantiomer by determining the optical activity and making sure it's right. And determine the rotation looking through a polarimeter. Okay, Fisher projections, spelled with a C. Fisher projections. We'll take a 2-minute break. We'll start working with Fisher projections. I'll pass back the lab reports from the Monday, Wednesday lab. And any questions about the lab tomorrow? Bromination of transtylbene. Be your first synthesis lab. We'll start with a compound called transtylbene. It's an alkene. We'll be reacting it with elemental bromine, Br2. Make a dibromide. There's different stereochemical outcomes though. Any questions about the lab?
Is the sheet for the lab we did yesterday been sent?
No, it will not be due tomorrow. Tomorrow is your unknown. We'll make the recrystallization answer sheet due this Friday for both labs here in class.
When is the Tuesday, Thursday lab getting lab report back?
Hopefully tomorrow. I'll pass these back. If you want to pick it up here, please yell. Grades range from lots of 8s. We have 10. Below was 6, I believe. 6 out of 10. Kimberly.
Yes.
Dominique. Shireen. Kate. Charlotte. Jonathan. Tassim. Here. Rosalind. Thea. This was just section A. Section A. You should put the section that you're registered for, not the lab you're coming to. Jonathan? Okay, guys, any questions? Any questions? Questions about lab this week? Questions about lab today? We'll meet here 2:30. We'll have some lecture. We'll be doing the recrystallization lab. So we'll have a pop quiz at some point this week. Test is Monday. Okay. And we're back. Fisher projections. Fisher projections is a way to show chirality, chiral carbons, chiral compounds, other than a perspective drawing. Sort of analogous to how Newman projections was a way to show rotations, conformations. Fisher projection, we use a crosshair. Just like this. And this is a chiral carbon. Okay? But when we do this, there's some implied stereochemistry here. Okay? This equals the bonds on the side are coming out at you. And so it's like this. The bonds at the top and bottom, that's kind of like a bow tie. Bow tie kind of coming out a little bit. Or like cat whiskers kind of coming out. You may see this. Top and bottom is implied things are going away. Okay? Make that look good. So the crosshair is implied. We can draw these in a Fisher projection. We should have a model here. Bromine, chlorine. Hey, this looks like bromochloroethane, like we started with. Let's see here. Methyl straight up. H in the plane, okay. Chlorine forward, chlorine green. Bromine going back. So is that it on the board? Methyl straight up. H in the plane going straight in the board. Yeah. Okay. We'll do it in a Fisher projection. Before we do that, though, is this RS? Because we do have a chiral carbon. What's the configuration? R or S?
You need to put the H in the back or look at it.
Bromine is 1, chlorine 2, methyl 3, H is 4. Is the H forward or back? If it's back, we can just do, if it's forward, we can reverse it.
It's in the plane.
Oh, it's R.
How's the H projected?
Over.
Now the H is not forward, it's
So
in
It's in the
the
plane.
plane. How do we do this?
Shift it so it's not in the plane.
You have to bend the R forward.
Can you shift everything?
The answer is S.
Did you just ignore it in this case?
No, you have to look at it from a little bit different view. Question?
I was gonna ask if you, like, acted like you were looking at it from this way.
Yes. You look at, if we stand over here and look through here, the H is going away from us. With the H going away, let's kind of move out. Where's bromine if I'm over here?
On your left.
It's one to behind the wall. So it's over at 9 o'clock. Where's chlorine? Over here at 3 o'clock. And then where's the methyl? Top. So we're going from 9 to 3 to 12 noon. With the H back, we're going counterclockwise, S. But I would first draw it in a Fisher projection, because the Fisher projection is exactly what we just looked at. Because we can draw like this. I've got a methyl coming straight up. Let's put an ME here. The methyl is straight up. Okay, what's going straight down over here? No, the bromine's going hydrogen. What's coming towards you guys? Chlorine, which is on the right. And what's going, if I'm over here, to the left?
Bromine.
Bromine.
But I thought
Do what?
you said the two sides are coming towards you. Bromine's not coming towards you.
Yeah, they are. You see how both of these atoms are coming towards the little man?
Well, if I look at it from that way, I'm
If you look at it from what way?
the little man's perspective.
That's what we're drawing. We're
But
drawing
if
the
I
little
look
man's
at it from
perspective.
my way,
That's. Do what?
she said, but if she looked at it from
This way, it doesn't. We're trying to make it so the H is in the back.
Okay, here. Let's try. Let's put the molecule up here. Methyl straight up. H going away. Chlorine is green. Okay. There it is on the board. Okay. Now, really, the little man needs to be sort of turned a little bit. I'm just going to turn him a little bit, and turn him like this, and look through kind of like that.
Get you a 3D set.
And make this the ground here. Okay, now let's look. Methyl straight up. Okay. There's what I see. Now if I go down, I kind of see, instead of me going down, I'm going to do like this. And so it's like that a little bit. But look, here are the two halogens. Do you agree that they're coming towards me? You see them coming towards me? Yeah. Now look at the methyl. Okay, I sort of, I did this so I could do this a little bit. How's the methyl? Coming towards me or going away? It's going away. And the H. What do I see? Well, I drew it right here. There it is on the board. The things on the sides are coming out at you, which is what we erased it, right? And the things at top and bottom are going away. The power of doing this is we've changed our view. But now we have it on paper. Because if you just stand over here, it's all in your mind. We put it on paper this way. Now do RS. Bromine's 1, chlorine's 2, methyl's 3. How's the H? Forward or back? Going back. That's what that means. Now we don't have to worry, is it forward or back? No, we drew it there, so it means that today and in 10 years, this is going back. So that going back, we have what? Counterclockwise S. Okay? Shown in a Fisher projection. Typically in the Fisher projections, you put the dash and the bold is going to be on the side. Okay? For example, here, draw that guy in the Fisher projection. And don't cheat. I'll tell you how to cheat in a minute. Dash and bold on the sides. You want them coming towards you. Little man's going to be over here.
Wouldn't you just flip the two on the side?
Oh, you want to cheat? See, once we did one, then you can sort of adjust from then on. Do it from scratch, though.
I did, but after I did it, that's when I realized what the cheat was.
Okay, good. If we're over here, right, I got 4 things on the carbon. What's going straight up on the carbon if we're over here? Methyl. What's going straight down? Yeah. Now both of those, if we're standing like this, both of these are kind of going away from me too. Okay? Because if that's the, okay, see they're both going away from the straight up point. Let's get rid of that. Coming straight down is H. What's on my left? If I'm over here looking at this carbon? Chlorine. And what's over here? Bromine. Okay, is it R or S? By the way, it's the same compound, but it's just potentially a different configuration. Or is it the same? H is what? In the back? 1, 2, 3. So what do we have? R. Yes, that's the enantiomer. That's the enantiomer. But you could have told that on the board, because there are drawn as mirror images. Aren't those mirroring on the board as drawn? Actually, now the Fisher projections are mirroring. Look at the 2 Fishers. Are they mirroring? Yes. Question.
Okay, so I just want to make sure. So if I'm looking at it and say my hydrogen, say if the bromine and chlorine were both pointing towards me, and my hydrogen wasn't there, so I can assume that it's pointing away from me. But when it doesn't have stereochemistry, it's in the plane, so therefore you.
I'm getting lost.
Okay, so you know how we.
Write it on your paper and let's look at it at some point.
Well, I have examples. Okay, so we didn't flip it on this one. Remember, we used to flip it from R to S.
Yes, if the H is, if the low priority group is forward, you can just flip your answer.
Right.
If it's in the plane, you can't just do that. You have to look at it in a different view. We're looking at it in a different view. I'm drawing what I see, really. What I see is actually drawn in a Fisher projection. Because I'm no longer doing dashed and bold. You don't do dashed and bold in Fisher. It's implied. And it's from a view from like this. We'll do more examples and clarify its usefulness. Show me what you're looking at a little bit later. Question?
So for the methyl group, since it's just like going up, but like how you said the dash is implied, does that mean that it's still going back, like how the hydrogen's going back?
Yeah, the methyl and the H are going back.
Okay.
I think I have to reverse this. Chlorine green, bromine blue, they're coming forward. The methyl's going back. See, here it's drawn straight up. The straight up is implied that it's really going back. And the H is going back. See, really nothing is in the plane in your Fisher projection. You got 2 things going forward and 2 things going back. The carbon is just sitting there, nothing else in that plane. Okay, that's Fisher projection with 1 chiral carbon. Let's see what's on the next page. Compounds with more than 1 chiral carbon. How many stereoisomers are possible for the following compound? Here, how many stereoisomers possible?
4.
For the previous compound, there was 2. How many possible here? First off, how many chiral carbons?
2.
2 chiral carbons. A chiral carbon is an example of a stereogenic site. That is, it gives rise to stereochemistry. And you have different options like R or S. An alkene is a stereogenic site. Sometimes, not always. Because an alkene could be cis or trans or E or Z. Two chiral carbons. Maximum number of stereoisomers equals 2 to the n, where n equals number, is this written somewhere? It seems like it should be. Number of stereogenic sites. How many stereogenic sites in the compound? 2. 2 to the n equals 4. How many stereoisomers are possible? 4. Max. It sometimes could be less. We'll have to identify when it's less. Could be less. Here the answer is 4. Okay, draw all 4 of them. And label the chiral carbons in each one. Do you want me to get you going? Let's draw the first one. How about if we do that and that? There's 1. What if we do boop, 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 and make that like that, and that like that? That's 2. Get the idea? No magic here. 1, 2, 3. Now we're going to have to maybe do this. And maybe, we haven't drawn that one yet. And the 4th one would be what?
Both of them back. That one back and forward.
All these have the same exact name. One question is, are these all different? I said max. How many different compounds did I draw?
3. Oh,
Are some of them the same, really?
yes.
Real quick. How many different compounds did I draw there?
No. Well, it's wrong.
No, that's 1 compound.
How many different compounds did I draw here?
It's 1.
The answer is not 3. The answer is either 1 or 2. How many different compounds did I draw over there?
2.
1. No, 1.
Here it is.
What was it?
Who says 1 compound?
Up the BR? Oh, it's only 1.
Who says that's 2 different compounds? Nobody? Yes, that's 1 compound. That's the same compound. Just because I changed dash and bold doesn't make a difference. Why is it the same? Do what? Why are they the same? How about now?
Still the same.
Same or different?
Same.
Different.
No, same. No, wait, no.
Different is called, thank you.
Yeah, now they're different. Now that's two different, now that's two compounds. Okay? These are the same. If you think they're different, then how would you distinguish them? RS? I mean, it's one bromopropane. I mean, it's two bromopropane. Both of them are two bromopropane. If you think they're different, then why? R and S? Well, if so, which one's R? What's the configuration here? Do what? There's no chiral carbon. Is this RS? Okay, that's one. Which is two? There's no answer. That's because it ain't chiral. If it ain't chiral, you can switch. It's the same thing. Because you can't say one's R and one's S. That should tell you that they're the same thing. Now, if we put this here, now they're different. Because now, this one is, what is this? That's S, right? And that one's R. Okay, now they're different. All right, over here, are these the same or different? Well, first off, let's do RS. What is this? RS. Okay.
R.
1, carbon with other stuff on it. 2, carbon with just there. 3, H is in the back, so what is this?
R.
R. All right, let's get rid of this. Chlorine is 1, carbon over here with other stuff. 2, 3, 1, 2, 3, H is in the back.
R.
R. Okay, let's cheat from now on. If that's R, what is this? It's the same thing.
R.
As long as the backbone is the same. It's the same exact thing. So what is this? S. Because when we changed from bold to dash, but kept the backbone the same. That's changing there. If you don't believe me, do it. Let's do it real quick. Chlorine 1, 2, 3. Clockwise, but the H is forward. So reverse clockwise to counterclockwise, S. You see, now we can cheat. If those are R, what is this?
S,
And this is,
S,
and this is,
S.
and this is,
R.
yes. You can check yourself, but keep the backbone the same and you just switch dash to bold, then you're switching. Okay, there we go. Are any of those the same in terms of R? I got an RR, only one RR, okay. We really need more room here on your paper. I've got bored, but let's draw these in Fisher projections. Fisher projections. I'm going to do it down here. Okay. We have 2 chiral carbons. By the way, hopefully that gives you the answer. They're all 4 different. Actually, that doesn't give you the answer yet. It doesn't prove that they're different yet. It doesn't prove it quite yet. Fisher projection. 2 chiral carbons, so we're going to do this like this. 2 crosshairs. Okay?
We can't s- Oh,
Now, we got to decide, this is the 4 carbons. 1, 2, 3, 4. Here it's horizontal, here it's vertical. Let's put this at the top. Let's call this A, B, C, and then D. So A we're going to put at the top. We could have did it the other way, but just, okay. So that's A. That's D. Now, the A methyl here at the top is going away from us, yeah? We need to look at this with it going away from us. So where do you want to stand? Over here. Where's the ground at? That's important. Always keep your feet on the ground. Is the ground near A or D? D. So we're going to say the ground is here. Standing on the ground, we want to look at this with A going away. So can I look through there? Now with A going away, I'm not hovering up here. Here's the carbon, but A is going away from the carbon. With A going away, is the OH on my left or right?
Right.
It's coming towards you guys. Correct? It's bold. It's coming towards you. All right? It's sticking out like this. If I'm up here and it's sticking out, it's on my left. I see it on the left. I just want to draw a methylene up there. It looks bare without it. Okay, what's on carbon, this carbon going to my right?
Hydrogen.
Yes. So there we go, we got that carbon on the fission. Now let's move down to the second chiral carbon, which is A, B, C, D. C. A, B, C, D. This one. Got a chlorine. Which side's the chlorine on? Which side is the chlorine on? Is the chlorine on the left? Who says left? Who says right? Yeah, it's on the right. Why?
Now that you look at, if you look at that, it's pointing towards you, so it's pointing towards the man.
This D-methyl is away from us. With the, that's what I'm saying. With the D-methyl away, which side is the chlorine on? If I'm over here, this methyl's not going away from me.
So you gotta rotate.
You could rotate, your book will tell you to rotate that. I instead move my little man over here. Keep my feet on the ground and look through here. If I'm over here, this methyl is going away from me. With that methyl going away, which side's the chlorine on? It's coming towards you guys. It's on my right. With the methyl going away, the chlorine's on the right. Keep your feet on the ground, because sometimes I see answers and it's like, well, you got your feet in the air. Feet on the ground. Question?
Could it, could you also explain it because of the red marks because they're trans?
No, they're not trans. Nothing's trans here. Maybe as drawn, but you have free rotation. Free rotation. Okay, let's do one with models real quick. Let's do this compound with a model. We need extra carbon. I didn't quite understand the question, but I don't see anything trans. You mean the methyls are trans?
We have a OH and a chloride for like different directions. So one's going
Well,
to
they're both folded. They're both coming towards you. Okay, let's put it down here. With the methyl going away, the chlorine's on the right. With the methyl going away, the OH is over here. Methyls are going away, top and bottom. There's the Fisher projection that we drew on the board, how it's supposed to be implied, okay? Is it the same up here? Well, let's look. Let's turn this like this. Oh, but that's green. We got to come over here. Chlorine is green. Okay. There's the zigzag on the board. See the methyl, boom. The methyl, all that's in the plane on the board, drawn this way in the perspective. The OH is coming forward, and the chlorine is coming forward. So you see it's the same thing. These are the same exact compounds. How did we get there? Okay? I came over here, and I looked through here. Little man. I'm just going to come in there. Looking through here, the methyl's going away. With the methyl going away, the OH is on the left. I mean, I could draw that. Methyl going away, OH on the left. That's what I drew here. Now, if I'm here, I can't look at this carbon because the methyl's coming towards me. So instead, I came over here, kept my feet on the ground, and with the methyl going away, chlorine is on the right. Okay? This had to be twisted because I had a different view up there. There we go. Let's draw the others in Fisher. Now you can actually cheat. Once you get going, you can cheat. This one over here. Boom, boom, boom.
Would you prefer us to draw on the metals like that so you know that?
Yeah, it looks a little naked without it. Drawing the methyls. Okay, let's don't cheat this time. Let's don't cheat. Again, we're putting methyl A and D. This is A and D. That is, the OH is going to be above the chlorine. The OH is here. Which side's the OH on? If I'm over here, ground's down here by D, looking through here, with the methyl going away, the OH is on the left. H is here. What side's the chlorine on? Well, we're going to look at this with the methyl going away. With the methyl going away, feet on the ground. The methyl going away, chlorine is going behind the wall. So it's on my left. With the methyl going away, chlorine's on the left. Methyl going away, chlorine's on the left. There's a Fisher for that. You see, they're different. Here, these two big groups are on opposite sides of the Fisher, but here they're on the same side of the Fisher. That actually has terminology. When your high priority groups are on opposite sides in Fisher, that's called 3O. When your high priority groups are on the same side in the Fisher, that's called what? That's called erythro. How do I remember that? When you draw an E, you put all your lines on the same side of the vertical. Yeah? They're on the same side of the vertical, like when you draw a capital E. When you draw a capital T, you put that on one side of the vertical, and you put this on the other side of the vertical. So you have things on opposite sides of the vertical when you draw a capital T. That's how I remember the erythro and 3O. Okay, let's draw the third one here. This one here. By the way, did you see what did not change in going from these two? Nothing changed here. Right? You see how these same? The chlorine is what changed. The chlorine changed from this side to this side. At this point, we can kind of cheat. We'll do more examples down the road where we can't cheat. But for example, this one will be what? Where do you want to put the OH at?
On the right side.
Well, you see that the OH is now flipped. As long as you keep the backbone the same. The OH is over here. Where's the chlorine at? Same as that one. So it's here. Those are H's. Erythro or 3O? 3O. It's also 3O. And then the fourth one, you need to go back and look at this from scratch and make sure you get this answer. Fourth one would be what? The OH is the same, so the OH is over here. Chlorine is different. That means the chlorine is now over here, and this is erythro.
But chlorine is on
It's opposite of that one. It's the same as the first one. Yeah. There are your four drawn in Fisher projections. What's the relationship between the four? It's a D. Let's call this Roman numeral 1, 2, 3, and 4. That's it. What's the relationship between 1 and... Hold on, let's do this one first. What's the relationship between 2 and 4?
They're mirror images.
Who said that? 2 and 4. They're mirror images? I agree with that. Does everybody see? Can you see them? 2 and 4? By the way, it's much easier to see their mirroring when you're drawing the fissure. Up here. Can you see them mirroring here? Not as easily. Although you do know if RS looks in the mirror, what will it see? SR. It's easier to see them, though, mirroring in the fissure. Yes. 2 and 4 are mirror images. Okay. Are they the same or different? Everything's got a mirror image. Except a vampire. Just because it has a mirror image doesn't mean it's different. Question. 2 and 4 are mirror images. But are they the same or different?
Yeah.
Wouldn't they be different because if you lay them on top of each other?
Okay. 2 or 4. Let's get them both here. This is methyl's back. Both groups on the same side. That's that one. I need to build. Green, blue. Methyl's back. That ain't gonna work because I got the, oh, that will work. Chlorine is green. Methyl's back. Both on the same side. They're both erythro. That's that one. This is this one, chlorine green. Methyl's back. Methyl's back. Okay, are those mirroring? Can you see them? Are those mirroring?
Yes.
Yes, they are. Are they the same or different? Well, will they superimpose?
No.
I mean, I could. They won't. I mean, I can't stack it. If I want to make the green go down like that green's going down so I can stack it, I got to. It won't stack. It's like they're mirror images that won't stack. They're different. It's like hands that won't stack. These are enantiomers. 2 and 4. Make it clear on your paper. These are enantiomers. 2 and 4 are enantiomers. What's the relationship between 1 and 3?
Same thing, right?
1 and 3, they look like they're mirroring. Do you see that 1 and 3 are mirroring? Easier to see in the Fisher projection. Yes. 1 and 3 are indeed enantiomers. We could build models too, and they would not. 1 and 3 are enantiomers. Let me ask you this. How can you look at a compound and tell it's going to be chiral? That is, it will have an enantiomer. You look for Waldo, right? What do I mean by Waldo? Plane of symmetry? Does 1 have a plane of symmetry? Is that a plane of symmetry? No. There's only going to be 2 to look for us. What about here? Is that a plane? No. No plane of symmetry. The mirror image should be different. 1 and 3 are enantiomers. 1 and 3 is called a DL pair. Because 1 will rotate light one way and 1 will rotate light the other way. 2 and 4 is a DL pair. You got 2 DL pairs up here. Question though, what's the relationship between 1 and 2? Are 1 and 2 mirror images? No. Because a mirror image of both of these on the same side would be both of these on the same side. These are, you're looking at the flow diagram. Question, are 1 and 2 stereoisomers?
Yes.
Yes.
Don't be so quick. These are all stereoisomers. These are all this compound with the same connectivity, just drawn with different projections. These are all stereoisomers, yes. 1 and 2 are stereoisomers. But are they mirror images? No. Stereoisomers that are not mirror images are called diastereomers. Diastereomers. Mirror images that are not stereoisomers. Where did we see this at? Where was the flow? Was that on the white? Yeah, I think it was white. Here, stereoisomers, there's 2 types. Enantiomers, these are mirror images that are different. Diastereomers are not mirror images. Diastereomers is kind of a default category. Stereoisomers that are not mirror images. Examples. What are examples of enantiomers? You can distinguish from them by RNS or DNL. What are examples of diastereomers? Erythro and 3O is a diastereomer relationship because look, this is 3O and that's erythro. They're diastereomers of each other. What were enantiomers? 2 and 4? Well, they're both erythro. Because the mirror image of erythro is erythro. And the mirror image of 3O is 3O. 3O and erythro compared to each other is a diastereomeric relationship. So is cis trans.
What is meso?
Meso is where we're going to be next. Let's repeat the process using this compound instead. I want you to do this on your own. We'll look at this first thing tomorrow. The entire process, draw each one in Fisher projections. You might want to get different pieces of paper. Start just like what we did, maximum number of stereoisomers possible. Draw them all. You've got to be careful. You may end up with some of them being the same. Because ultimately, just because it's a mirror image doesn't mean it's different. How do you tell if the mirror image is the same or different? You could superimpose, or you could look at the structure and find Waldo. Because if you find Waldo, then the mirror image is the same. Trust me. Something that has a plane of symmetry, the mirror image is going to be the same. And if it's the same, it ain't 2 compounds, it's really only 1. Repeat the process there. Let's see what we can do to finish up today. Questions about other questions? So we're bringing in the idea of enantiomers, yeah, but now we brought in diastereomers. Fisher projections. Questions?
So the reason that we're viewing the chiral carbon with the methyl away from us is so that it's not coming towards us? Because before we were bringing the hydrogen with that, because it was the...
Well, it's because we're going to draw it in the Fisher projection. But we're putting the methyl down. If we put it down, it means it's going away. So we want to, if it's going away, we need to look at this with it going away. Because we want to draw it with it away. And we're saying with the methyl away, the chlorine's on the right. That's what this means. The methyl away, what side's the chlorine on? With the methyl away, I got to stand over here for the methyl to be away from this carbon. It's away. With the methyl away, the chlorine is coming towards you, so it's on the right. The methyl away, the chlorine's on the right. The methyl away, the chlorine's on the right.
I guess what I'm asking is why don't we choose for the hydrogen to be away from us rather than the metal?
Okay. It's easier for the thing in the plane to be away.
Okay.
Because I can stand over here. With the H going away, well, it is going away. How would you draw that? The H going away.
So I guess your person would be where you are. So
Yeah, but then I've got, so what am I going to put straight up? The H going away, and what bond is also going away? Because look, from here, that bond's going away and this bond's going away. That's what it means. These are going towards us. The H is going away. What other bond's going away? Up here, nothing.
So it's always going to be a methyl that we're choosing?
No, we'll do more examples, and in the examples it may have some definition requirements. Usually you put alkyl groups at top and bottom, and you put heavy atoms or big substituents on sides. That's the way I set this up. We'll learn how to rotate this. You can rotate this just like we rotated Newman conformations. 3 at the top can rotate. We'll do more examples going forward, including on that warm-up page. The warm-up page on the right, on the white. There are questions, and of course there's questions in the workbook. So from this point, start working questions, problems, and then questions will arise. And tomorrow when I say, okay guys, any questions? And be ready to say, yes, on number 6 on page whatever, how do you do this? And then I had a dream one night where I said, any questions? And everybody raised their hand. Believe it. And then I had a nightmare where I said, any questions? And everybody was like, no, I don't have any questions. Okay, see some of you today here in the lab, right here.
Do you want us to not do that based on
That one will have miso. We'll have miso. We'll need to introduce miso.
We don't know what that is.
Miso is a compound that has chiral carbons, yet as a whole it's not a compound. I said earlier that it has multiple chiral carbons. One is going to be chiral. That's two.
Like,
Where's Waldo?
they might all,
We have chiral carbons, yet still have planar.
they might all cancel each other out, but look at one.
Always look for Waldo.
Yeah.